You got it.
Good morning, everyone. I'm in the midst of grading your all's crop projects. So far, had some really good ones there. So at the end of that, it should open up to where everyone will have a chance to review everyone else's crop project. And here in a few days, I'll open up the second phase of that, which basically I'm going to try to pair you up with someone that you'll have to communicate with to kind of collaborate on a multimedia presentation, comparing and contrasting your two crops. And I'm going to do that based on the crops that you all chose. So I'm going to try to match you up in a way that you can really compare it and contrast it and hopefully generate some good conversation about that and learn from each other. A couple of people had some issues with the midterm, and I've opened that up to people that have reached out. If you had a problem with it, just let me know today. I think I want to try to get all that wrapped up as soon as possible, considering that we're well past the midterm at this point. But my fault in taking so long to get that up. I know you're just finishing this test, but we probably need to have another test too. Just because we've covered so much since then, and rather than break it up into midterm and final, where the final is covering up so much more, I think it's more logical to break it up into three decent sized chunks, a little bit more easy to consume that way. So stay posted on that. We'll communicate, let you all know when we're ready for the next one. But we're going to go ahead and transition into chapter 12. And this week we'll be trying to cover two chapters, both 12 and 13, to finish off unit 2 and start on unit 3. So today we'll be talking about water and the relationships that plants have with water, which, as we know, are very many. Is the majority of most plants, the majority of most water, I guess, depending on how much you drink, which I think I probably need to top my water per day. And we talked before about how we're looking at climate issues they're creating. But either way, water makes up the majority of the plant's mass, up to 90% and over in some cases of the tissues in plants are made up of water. Of course, it's required for the seeds to germinate. It allows the plant to stand up through turgor pressure, and it's carrying the minerals and nutrients into the plant as well as throughout the plant. It's also used to transport all of that photosynthate that the leaves are producing through photosynthesis. All those metabolites, all those secondary chemicals, they're able to move that to other parts of the plant when they need it, whether that's to the roots or to the stems, secondary tissues. And also water being transported through the plant not only holds the plant up, but also cools the plant through kind of evapotranspiration, a combination of the stomata on the leaves opening up and releasing that water and oxygen through respiration, but also the transpiration. So it's moving throughout those pores, but then also evaporating from that water vapor, escaping, and then evaporating allows it to cool the plant. So if we don't have enough water, then first we'll have a delay in plant growth. It'll be inhibited. Eventually, the plant will begin to wilt, and there's a temporary wilting point, which plants can recover from. You supply the water that they need, and they're able to stand back up. And that's really through that whole idea of turgor pressure, of the water moving from whatever media, the soil, up into the roots, up through the plant, and out through the leaves. That process allows it to stand up. And if that process is inhibited, then the plant wilts. And if it wilts beyond the point of repair to get to the permanent wilting point, then the plant will die. So almost all the water that we get for plants to be able to function is coming from the soil through the roots. There is a small amount that can be taken up through the leaves. Not very much, but that can be a way that if you have a plant that is wilting, if you kind of miss the leaves, it will kind of regulate the opening of the stomata, and there can be a little bit of water taken in through the leaves and stems, especially in particular species of plants. But most of it is taken up through the soil. What if a plant is not growing in soil? Like a Tillandsia, the air plants, those don't require media. In those cases, the plants have special tissues and organs that allow them to take it up through the leaves, or sometimes aerial roots, or into the stems. So let's take a look at some of the unique characteristics of water that not only makes it crucial for plant life, but really all life on Earth. First, water is what we call the universal solvent. And being a solvent, it can dissolve pretty much anything, more substances than any other liquid known to man. So when you dissolve something in water, it becomes a solution. So water is the solvent. Together with whatever is dissolved into it, it becomes a solution. And that plays a huge role in the soil as the soil solution. It's not really just H2O anymore. It's H2O plus whatever other nutrients you have in there, charged ions. Water is also one of the most stable compounds. And for a long time, before we had a good understanding of chemistry, it was considered a single element rather than a molecule comprised of two different elements, two hydrogen atoms, of course, attached to one oxygen atom. And if we look at the way that that molecule is arranged, it has these special properties because of this arrangement. It's stable and strong, partially because of this 105-degree angle here between the hydrogen atoms. It's not symmetrical, it's asymmetrical, which gives this polarity that gives one end kind of a more positive electrical charge and one end a more negative charge, because of the way that the ions, the electrons, are arranged. So when we look at this schematic of the water molecule, in the center are protons. So hydrogen has one proton, one electron. And if we look at so it only has one of these kind of shells, and they call these kind of like your valence shell. And valence is the ability basically to share electrons. So if we look at the oxygen molecule, then it has 8 electrons, 2 of them on the inner shell, 6 of them on the outside. So it shares electrons with hydrogen, which allows it to become stable and have this complete shell of 8 electrons on the outside, which also gives it that strength and stability, and allows it to stick to other water molecules, allows it to be that universal solvent. And it also gives it some other unique properties, such as surface tension. And I'm sure you've probably seen this in play before. It's just this physical property that allows water, while it's in its liquid state, due to these intermolecular attraction between these hydrogens bonding between the water molecules themselves, but also to other water molecules. And together they kind of stick and make this almost like film on the top of the water, that gives it this really strong surface tension. And I think the best way to kind of imagine surface tension is to look at these fisher spiders. If you're arachnophobic, maybe screen too long, but at least take a look at how these fisher spiders are able, I mean, they're pretty big, right? They're large spiders, but they're able to distribute their weight outwards so that they can almost like float on top of that surface tension of water, the film of water. And then when they are fishing, they're actually going to dive down for their prey, then they kind of contract their body, put all their weight in one place, and they go underwater. So there's just an image of surface tension, distributing that weight evenly. And that idea of surface tension is also why if you were to do a belly flop, for instance, then it's very painful, right? Or if you are to dive from a very tall height, and the more of your body that hits that, the more painful it is, because the more resistance you're getting onto that surface tension. All right, so one of the other really cool things about water is something that we're all aware of course, that it has multiple phases, and it's one of the few molecules that is able to exist as a liquid, a solid, and a gas. In its liquid state, water kind of has this attraction of the molecules kind of being somewhat chaotic and random all over the place. But then when the temperature gets low enough and water shifts into its solid phase and it freezes, then you actually get this really kind of beautiful, symmetrical, rigid lattice of this open kind of porous structure that forms. And that, gives it this strong, solid state where, I mean, really there's lots of different, good things about water in its solid state versus its liquid state, different properties. When it becomes ice, it has this rigid form, but also gives it this additional strength of structure that can be very good for us in agriculture in terms of freeze and thaw cycles, opening up pore spaces in the soil, which then allows better infiltration and percolation of water through the soil profile. Water also has very high specific heat, and that allows it to absorb temperature, absorb heat, and also it allows it to stay cooler. So one thing about having moisture in the soil is that it then becomes more thermally active. It can store more heat over time. So going back to the climate again, thinking about like microclimate. If you have moist soil, then that becomes a thermal mass and a place where you can absorb additional temperature. And that can kind of work both ways, for the better or for the worse. If it's warming up, it takes more temperature to warm, but it stores it longer, so it stays warm longer. So if you have moist soil later in the season, then you can kind of delay freezing of the soil and work the soil longer through the season, as long as it's not too wet anyway. On the other end, in the spring, you kind of want the soil to dry out so that it doesn't stay colder longer. And then when you have the sun finally coming out, adding that water so you can get that thermal mass. So anyway, water, very high specific heat, so it's resistant to temperature change, and it holds that temperature longer. So here's a look at water and the different phases, and how the kind of intermolecular forces are lower in the kind of looser form and higher in the kind of more compact form. So it's low force in terms of gas, It's higher in liquid and higher still as a solid and ice. And it kind of works oppositely with temperature. So of course, low temperature, it's ice. Kind of medium temperature, it's a liquid. And then when it gets to the boiling point, it becomes a gas and then exists as a vapor. So let me try to see if I can zoom in on this for you guys just to see those kind of intermolecular forces in the arrangement. So as a solid in ice, it's basically this very formal kind of arrangement of this lattice, very rigid structure. In liquid, it's loose and somewhat random, and the molecules can actually move around. And then as a gas, they are moving very quickly and randomly. And so this plays a very important role in plant science in that we have these three phases. When water exists as ice in a plant, it's either frost on the leaves or breaking the cells up. Because as we have these intermolecular forces, causes some contraction and expansion as well. And so it's going to, in freezing, causes those cells to actually burst open. And because of that, kind of cytoplasmic streaming, all the liquid coming out of the cells eventually from frost, plant tissues will turn kind of black. Looks like they're burned, but it's just, and you get the same thing with, if you have steam on plants, it also looks like they're burned. It's kind of interesting to see that you have the same symptoms on either end. So how about water and how it is available? So we know that it's important in photosynthesis. We know that it's important for moving the mineral nutrients into the plant as well as around it. But how does it do that? So water is held by and moves within the soil to supply the mineral nutrients and oxygen to the roots, as well as just water itself. So pore spaces in the soil are always either going to be filled with water or air, or a mixture of water and air. If these pore spaces are filled with water, then we say that the soil is saturated. And that is not good for plants for a prolonged period of time, because then you don't have any oxygen in those, any air in those pockets. And without oxygen, then the plant's roots cannot respire. It can't take up nutrients. It can't even take up water if it's saturated, unless the plant is, adapted to growing directly in water. When the pore spaces are filled mostly with air, then the soil is too dry, because you have to have that water moving into the plant to be able to, to grow, to maintain turgor pressure, but also to move the minerals and nutrients. So we look at the ability of a soil to retain water as its water holding capacity. And water moves through the soil through kind of a variety of ways. First, we think of it as moving from wet soil to dry soil along a kind of wetting front. And in this image, they're comparing sandy soil to a more clay soil. And of course, the big difference there is the pore space. And clay soil is going to have more pores, but they're going to be smaller pores. Sandy soil has larger pores, macro pores, so water quickly drains. But we'll see water moving through the soil, no matter what type of soil it is, through this wetting front, where we're going to have wet soil behind it, dry soil in front of that front. But in this image, it kind of might be somewhat misleading, because it looks like water is just kind of moving downward. It can actually move side to side and actually even move back up, just depending on where those pore spaces are and how those pore spaces are arranged. So again, a sandy soil is not going to be able to hold as much water as a clay soil. So even though we think of clay, especially kind of in our region, the mid-Atlantic, we have lots of soils that tend to be kind of higher in clay, especially as you move kind of more inland into the Piedmont and into the mountains. We tend to almost vilify clay. I feel like has a very important role in holding water and holding nutrients in a soil. So here's just a look at the different capacities of the different texture components of soil for holding water. Sand can't hold it very long, and neither can silt. Clay can hold it much longer. So again, we really want to try to have a good mix of clay, silt, and sand. And that is what we refer to as that loamy soil, which I'm sure you guys were looking at in that lab, and kind of figuring out the clay, sand, and silt proportions of the soil. So we have three forces that are responsible for water actually moving within a soil. First is just gravity, and gravity is just pulling water downward. And that's what we mostly get when the soil is saturated. So after a big rainfall, or say you're flooding your soil for irrigation, we've got gravity pulling that water downward down through the soil profile, eventually into the water table itself. But then we have these two other forces, and gravity pulled soil really doesn't play much of a part in actually getting water to the plant. And that doesn't seem like it would make very much sense, but when gravity is actually pulling water downward, that water is not really available to the roots. It's only when that water is stored in the actual pores of the soil. And these result from the forces of adhesion, which is, think of adhesion as adhering, kind of like a glue in a way, or like a magnetic force. It's a force of attraction between like molecules. So soil particles are kind of gluing or magnetically holding water to them. That's adhesion. Cohesion is the force of attraction between like molecules, so water to water. And when we combine the forces of adhesion and cohesion, then water doesn't just move downward. It can move really in any direction. It can move up, it can move down, it can move side to side through these two forces working together. And we get this neat effect known as capillary rise that happens through the forces of adhesion and cohesion, which allows water to move upward in a soil profile, not just down, or laterally as well. So because of these water sticking to the soil particles, but then water sticking to water, it can kind of move in any direction. As the forces increase, as there's more, kind of pressure, and think of this like in this image, we're seeing capillary rise through kind of these different pathways, if you will, these tubes sticking into the water, and that's resulting from the forces. As the soil dries, the water film that surrounds each soil particle will kind of thin and give a greater force, which makes it more difficult for the plant's roots to extract water from the soil particles. So really, you can actually have water in soil, but you can still have plants, wilting if that, energy potential is just so high that prevents it from being able to, actually extract that water. And we look at these forces that act on the soil water in this kind of energy level as water potential. And we look at that as the same as we would for air pressure through PSI. So water potential is determining the direction that water flows. And like air, water is going to move from basically high pressure to low pressure, high, warm air to cold air, high water potential to low water potential. So we look at these different units of pressure as a way to kind of figure out how much potential there is and how you can get that water to the plants themselves. Saturated soil is going to have basically a water potential of 0, which means that it's able to be just pulled by gravity, it's able to move. Then it becomes more negative. And that soil water potential is determined by different factors. First, gravity itself, then we have the matrix potential. And the matrix potential is coming from the forces of adhesion and cohesion, both between the soil particles, but also water to water itself. Then we have osmotic potential, which is mostly caused by dissolved salts in the soil water and just in the soil profile itself. So salts occur naturally, but we add to them through a bunch of different ways, really. I mean, through actually working the soil, we change the concentration of the molecules in the soil, the way that they react with each other, and we can add salts to that in that way, or kind of influence the way that salts form. We also add them through fertilization and also just through irrigation water. So generally irrigation water is going to move down at the profile through gravity, but also upwards and laterally through the matrix potential of water sticking to water and water sticking to the soil particles. And then we also can have it affected positively or negatively by the osmotic potential through dissolved salts. So if you have water moving through an irrigation canal, it's open, right? So it's picking up, can pick up salts through that as well. Also through our filtration, our treatment of water, if we're using like a municipal water supply, then we're adding salts to it. Whenever we're adding like chlorine to water, we're doing that in the form of a salt because it can break down more easily and dissolve into the universal solvent of water. So we add salts to the soil intentionally and unintentionally. And they can be present naturally in the soil as well. So salts that are present in soil water will create that osmotic potential and this energy that if it is in a sufficient concentration, it can prevent water movement into the plant. So in this illustration here, in the beaker on the left, they added salt to that water, which creates that osmotic potential that gives this pressure that is too great for the plant to overcome. So it can't actually, even though it's sitting in water, it can't actually take that water up, which causes the plant, in this case, to wilt. On the right, we got pure water. It's readily available to the plant, doesn't have to overcome that osmotic pressure and potential. We can also use that reverse osmosis, though, as a way to filter water. And that's very useful. I mean, I think more and more people are doing that both in field agriculture as well as in the controlled environment too. So fertilizer itself is a salt and can inhibit water uptake if it's basically accumulates over long periods of time. And it's probably easiest to see in a potted plant in a container, and you may have even seen it at your grandmother's house, right? She got house plants in there, and over the years if your grandmother is anything like my grandmothers were, they had house plants and they would like to throw on the Miracle Grow to make them grow a little more, right? Make them happier. But over time, you'll see those salts accumulate and it will look like kind of a white, or in the case of Miracle Grow, a blue crust that kind of forms on top of the soil. And that's partially due to salts are lighter, so they can actually move upwards up into the soil profile as well, and kind of move with water too. But that can create that osmotic potential, which inhibits water uptake. It can also lower water potential enough to pull water even out of roots, which causes what we call fertilizer burn. And if you get like a powdered fertilizer in the salt form on leaves, then you'll get the same thing. So there's other issues that can cause fertilizer burn as well, but I think one of the most common causes of problems with plants in any form is either having too much water or too little water, or not the right type of water at the right time. So let's look at water moving the soil. In image A here, this would be after we've either added water through irrigation or after a lot of additional rainfall. This is saturated. And basically all of the air pockets in the soil are filled with water. And there's very little tension, very little pressure that is needed to remove the water from the soil particles. So it just flows downward through gravity when it's saturated. And that's why it's moving, because of gravity's pull. And that's why it's not really available to plants when it's saturated. And of course, when we have soil saturated, it can no longer take water at this point. So we end up getting water running off. So lots and lots of rain, you end up getting the soil saturated, and eventually it accumulates to the point to where there will be water, instead of percolating into the soil and infiltrating into the soil, it's just moving off of the surface, which could cause erosion if that soil is not protected in place. In B, the soil is beginning to drain after a period of first gravity pull. We get this air to water ratio increasing, and air is going to start to occupy some of those pore spaces. So at this point, after all of the water has gravitationally drained, you get what is called field capacity. And we have this water pressure, they say a third of an atmosphere, which is just a different measure of pressure. And field capacity is when water starts to become available to plants and plant roots. In C, soil continues to dry, and then that water film is becoming thinner so that there's greater attraction through adhesion of the water to the soil particle. So it's greater tension, greater attraction. It needs greater energy to actually remove water from the soil. So even though there's water in this soil, in this image, it's attracted so much to the particles of the soil that plants can't actually extract it. They can't overcome this pressure. So between 0.33 or a third of an atmosphere and 15 atmospheres. So this actually, in this image, it would be negative 15 atmospheres, because you'd have to overcome that pressure in order for the plants to be able to extract that water. So in this image, you'd start to get some wilt. Here's just another look at that movement of water and how it's retained in the soil, again, based on the textural components. So it's that the variety and I guess the structural form of the different textural components together that determines the relationship between soil water content and the tension of the soil, the pressure altogether. So again, we want some of each. We want some clay, silt, and sand so that we get a good variety, and it's a mix of kind of getting this equilibrium. So this right here, where we have kind of an in between sand, silt, and loam, this is the point, the breaking point where water becomes more available to plants. When you get to the point in which the plant wilts and cannot recover, we call that the permanent wilting point. And plants actually have available water between field capacity and really, maybe this image isn't the best because it should be, you know, the wilting point rather than the permanent wilting point. That's really truly available water to plants. And of course, we have this temporary wilting point where it just doesn't have enough water for a period of time. And then beyond that, it dies. So that's the permanent wilting point. Really, I mean, you're going to know, right? If the plant is no longer green, then it's reached that permanent wilting point. And of course, different plants have different adaptations that allow them to hold the water inside the tissues longer, whether that's a different photosynthetic pathway or maybe a thicker cuticle on the outside of the leaf, or maybe the stomata just not opening as much. So in this case, we have kind of an equilibrium of pressure between field capacity and the wilting point. Above field capacity, we've got water basically just draining off. So the plant will be healthy at this point as long as it's still gravitationally draining. At the point of saturation, though, then plants can also die due to not having enough oxygen. Again, depending on the adaptation of the plant. And it's also important to note that we can get wilt on both ends. We have too much water, we don't have enough oxygen, roots can't breathe, then they can't take up water. So they're sitting in water. You got water all around, but they can't drink it. So you get wilt on either end. And wilt, of course, negatively affects plants on both ends. Here's just another look at this in terms of pressure. So we get a greater pressure. At saturation, pressure is 0, but at field capacity, it's about -1/3. And between -1/3 of an atmosphere and -15 atmospheres, then you've got, you know, available water. Beyond that, you've got water that is so tense, so highly attracted to the soil particles that, of course, you can't get it. And they call this adsorbed water because it's adhered to those soil particles. And we need, again, that adhesion. We need it as well as cohesion to have available water, but water being in the soil, but just adhered onto that soil surface, as also called hygroscopic water. And plants just can't use it. So it's there, but they're not able to get it because of that greater pressure gradient. So again, we look at available water as that water that is between field capacity and the wilting point. Water is absorbed by the roots from the soil and distributed through the plant to the highest leaves, which gives it turgor pressure. Water is entering through kind of both active and passive forces. And we got this long kind of gradient of the xylem, that tissue that conducts water and moves it upward from roots to the stem. So, and eventually to the leaves. So you've got xylem going all the way down into the roots. And once water is in the xylem, it's basically, again, has a difference in pressure as it's moving through this kind of conduit of the plant, from the root to the stem to the leaves, and eventually throughout the leaves as water vapor into the air. Along with that water, we have all the dissolved minerals and nutrients that are carried to the different parts of the plant so that the plant can actually grow and still conduct photosynthesis. As water moves through this gradient of the plant through the xylem tube, basically have this decreasing water potential from the soil through the plant to the atmosphere. So it's decreasing, it's becoming more negative water potential. And that tension basically creates this turgor pressure that holds the plants up. So as long as that is kind of happening at equilibrium, water entering the roots and then exiting through the leaves and going through this xylem tube, as long as that water is continually sucked through, then it's going to be standing up and looking healthy. And once that ceases, that's when you begin to get wilt. So we call this the transpiration stream, and that movement of water from lower to more negative pressure gives it the turgor pressure, but also that evaporation or transpiration of the water from the leaves allows the plant to regulate its temperature as well. When we don't have enough water available for the plants to take in, then the stomata, those pores on the undersides of the leaves, are going to close to try to conserve water. And that's why the desert plants, cacti and succulents, can survive under really hot and dry conditions, or also cold and dry conditions. So osmosis, we kind of mentioned when we're talking about osmotic potential, is just the flow or diffusion that takes place through some sort of membrane. And in the case of plants, then it is a semi-permeable membrane. And when we talk about reverse osmosis, some of the purified drinking water that you might get in a water bottle is filtered through reverse osmosis. It's basically just going backwards through that membrane. And that is going to separate the solvent from the solution. So it's going to take whatever was in the water out of it. And in doing so, that's how the plants get the different nutrients. So we have this concentration gradient that creates this flow condition through these semi-permeable membranes, which really there's a lot of them. There's all kinds of different membranes in the plant, going from xylem to phloem, or xylem to one cell to another, basically. Think about it that way. And again, that movement through these membranes gives plants its rigid structure that we call, or turgidity, right? Or the turgor pressure. And without turgor pressure, the plant wilts. So this is also how the minerals are transported and taken to the places that they need through the plants. So plants are absorbing mineral nutrients against the high concentration gradient through active transport. And that active transport is basically facilitated by these specialized proteins that we started to talk about a little bit in that whole photosynthesis talk. So these special proteins in these plasma membranes are going to actually carry the nutrients that they need. And every single nutrient has a very particular pathway. It's got a special protein that allows it to bring these nutrients through these different membranes. And we'll talk about that in much more detail on Wednesday. I don't think it's important to know exactly what that pathway is for every nutrient. In some cases, for your particular crop, you might want to know what that pathway is. just because, you know, the different adaptations can help you clue into things like just issues with your plant, the abiotic, the, you know, basically what gives the plant its kind of optimum conditions. So this transport doesn't always, but often does require energy so that the proteins can move. So in this image, you know, we basically just got potassium is this black block. We got a potassium ion. And here it is, you know, first it's outside of the cell in the water solution. It's taken into the cell and then taken into this, you know, protein carrier that brings it into the membrane and then moves it throughout that membrane into the cytoplasm of the cell. And then it can return and take another one. So it's the process of, you know, photosynthesis that eventually leads to the creation of these proteins that allows nutrients to be moved in. It's kind of like what comes first, the chicken or the egg, the plant or the nutrient. So we got sugars moving throughout the plant. You know, water and the dissolved nutrients move through the xylem. The sugars, which we're thinking again of as photosynthates, all that stuff that is produced in the leaves through photosynthesis. These move primarily through the phloem tissues. So phloem for food, xylem for water. Even though in the xylem it's bringing up food in the form of nutrients, but it's just not in the right concentration that the plant needs. So it's fixing that. And really, plants are kind of like the original alchemists in a way, because they're changing soil nutrients through photosynthesis with the addition of light to the sugar that they need to survive, but also they need to create energy that moves up through the food chain and into eventually into our bellies. So photosynthetates can move. They're mostly moving from leaves into other tissues downward, but they can also move laterally and upward. So you can have source leaves photosynthesizing and, you know, basically taking that photosynthate and then moving it up to a new leaf, which would in that case be a sink leaf, as well as to all the other organs, so that plants can make flower buds, make flowers, make fruit, make seeds eventually. So this translocation of these sugars occurs through a variety of processes. First, we have diffusion, which is just moving these ions and molecules fairly slowly through the plant. And we've got cytoplasmic streaming, which transports the molecules and the ions within the cytoplasm, within that, you know, stuff within the cells, faster than diffusion. And then we have multidirectional mass flow translocation of material in the phloem itself. So all of these metabolites moving together through the phloem. And finally, we've got very rapid upward movement of water and mineral nutrients through the xylem. And you can really see that in a wilted plant. Let a plant wilt, add water to it, and just try to, you know, put a timer on it and see if you can tell how long it took for, you know, that plant to stand back up to maintain that turgor pressure again. Surprisingly, it's not very long. These, other than cytoplasmic streaming, diffusion, mass flow, and, you know, kind of upward movement are the same mechanisms that water moves through the soil as well. All right, so hopefully you all learned something today there about how water is so important to the crops that we grow and how it works within plants as well as outside of them. Anybody have any questions, comments, or concerns? All right, well, I hope you all have a great day. We'll see you Wednesday.
Okay.